Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, spring scales. When you put an object on a spring scale and let it settle down, the scale reports the object's weight. But the connection between the actual weight of the object and what the scale reports is not entirely obvious. There's a bit of stuff going on here, and it involves, not surprisingly, a spring. Since it involves a spring, I'm going to start by looking at how springs behave. So, turns out there are lots of kinds of springs. I have here one that might be called a compression coil spring. I mean, it's a coil spring, so it's wire wound into a coil, and it's designed really so that it's springy when you try to squeeze it. This is also a coil spring, but it's a tension spring. It does its trick when you try to stretch it. Actually, you can stretch this guy too. You can't compress this guy because it's already as tightly compressed as it can get. But there are lots of other kinds of springs. There are flexure springs that just bend. Here, this stick, believe it or not, behaves like a spring when you bend it. What else? The world's full of things like that. I mean, springboards are springs for diving. This table behaves as a spring when I push on it and try to bend it. So anyway, springs are everywhere. And one of the most interesting properties of a spring is that when you distort it away from what I call its equilibrium shape, the shape which it adopts when nothing is pushing or bending it, whatever. If you take it away from that shape, it develops what are called restoring forces or restoring influences that push it back towards its equilibrium shape. So this spring has an equilibrium shape that looks just like this. This is what it wants to be when it's left alone. And if you compress it away from its equilibrium shape, it develops restoring forces that push back on its ends, trying to cause them to accelerate back toward the equilibrium shape. And not just when you compress it, if you stretch it, again, it's not really designed to be a stretch tension spring, but you can do that, it fights back as well. And if you bend it, it's not really its intention here either, it also develops restoring forces, or maybe they're torques, trying to go back towards its equilibrium shape. So that's the first observation about springs is when you distort them away from their equilibrium shape, they develop these restoring influences that push back. So how strong are those restoring influences? The amazing thing is they are typically proportional to how much you have deformed the spring, how much you've taken it away from its equilibrium shape. How far, what angle, all those things. And that behavior is known as Hooke's law. It's empirically observed, and it certainly was several hundred years ago when Robert Hooke discovered it or identified it. What that means then is if you take this compression spring and you compress it by 1 unit of length, let's say 1 centimeter, so there's about a 1 centimeter compression, it is now pushing back on its own ends with a force that might be 1 unit of force. If I compress it 2 units of length, it pushes back with 2 units of force. 3 units of length, 3 units of force, and so on. That's Hooke's law. There's a proportionality between how far you distort the thing and how hard it pushes back towards its equilibrium shape. That works for a stretch spring. You stretch it 1 unit, you get 1 unit of force. 2 units of force, 3 units of force, and so on. Same with the flexure spring. 1 unit, and so on it goes. There is a limit to Hooke's law in virtually any context, any spring you encounter. If you try to distort that spring too much, you go beyond the limit of Hooke's law, the Hooke limit, you get permanent, 2 things that happen. First off, the restoring force or influence in general is typically weaker than it would be in terms of proportion. It doesn't quite keep increasing the way you expect. And accompanying that failure of proportionality is typically permanent damage to the spring. It usually doesn't recover anymore. You go beyond the hook limit and you get permanent deformation of the spring. For example, if I compress this spring, it probably will work all the way until it's smashed flat. But certainly if you take a spring like this and you pull on it, I can't do this with my hands, but if you pull on it hard enough to stretch it into one straight piece of wire, it will never go back to this spring shape. It has been designed and manufactured so that you'd have a tough time getting it to forget the spring shape. The spring shape has been programmed in it beautifully by material science. But you can go beyond the limits and ruin it, and it will never recover. This one, you probably can't do it by compression because you can probably get all the way down to a flat coil and it will still recover perfectly. But if you bend it or if you pull it out, you can ruin it too. Okay, so that's the world of Hooke's law. How does that help us with a spring scale? Well, what the spring scale does is, knowing that Hooke's law has this behavior, the springs have this Hooke law behavior, it uses a spring to support the object you're weighing. So when I put a book, this book, the old edition of Encyclopedia of Physics, if you put that book on the scale, what happened inside that scale was there's a spring that's doing the support, and that spring changed shape. I don't know whether it got compressed or stretched or bent. We'd have to open the scale up to see what the spring looks like and how it's being distorted. But I know it is being distorted. And the spring is distorting until the scale is perfectly supporting the object. So I can play spring scale here with that big spring. I have to center the book nicely. Can I pull this off? It's tough. But right now, the spring is pretty much supporting the book. I have to keep the book from tipping cockeyed over. But look what's going on here. The book has a weight. The weight hasn't changed throughout this entire story. It's always the same value. And if that was the only force acting on the book would fall. And I can show you. So I can take the book, let go of it, it falls, right? So I don't want to do that. So I want it to support it. And so now the book is being supported not by me really, although I'm having trouble getting it to balance perfectly on there. It's being supported by the spring. The spring is pushing up on the book with a force that cancels the book's weight. So we know exactly what that upward force of the spring is. It's a force that is, of course, upward, but it's exactly the same amount as the book's weight. So if the book weighed, the book weighs 29 newtons, that spring right now is pushing up with a force of 29 newtons, canceling the book's weight and allowing the book to be inertial. Object, in this case, an object at rest, staying at rest. Well, we know that this spring has the characteristic described by Hooke's law that its distortion away from equilibrium, from its equilibrium shape, is proportional to the force that it exerts on its end. So if we know how this spring behaves, for example, that it exerts 1 Newton of force upward on its end for every 1 millimeter we push down on the top and distort it. Suppose that there's an upward force of 1 Newton per millimeter of downward compression. Then if we compress it down 10 millimeters, we get 10 newtons of upward force. And if we compress it down 29 millimeters, it will push up with 29 newtons of force, just enough to support the book. So, if we know that the spring's characteristic, which is a process involving calibration, we know how that spring behaves. In that case, we can weigh the book by using the spring to support the book, to get basically cancel the book's weight, and then we go and measure how much is that spring distorted. If it's distorted 29 millimeters, we know that it's pushing with 29 newtons of force, just enough, evidently, to support the book's weight. The book must weigh 29 newtons. So that's what a scale is doing. They have calibrated its spring. It's got a spring in there. I don't know what the spring looks like. Maybe this, maybe something else. But this spring pushes up on the platform with a force that's proportional to how far the platform has been pushed downward, distorted downward. And you can see it actually does distort downward. Let me push on it with my hand. You can see it's going down. And as it goes down, the dial needle varies, because what that dial is really telling you is how far the spring has been distorted. And everything has been set up so that if the spring distorts this far, that means we've shrunk the spring a certain distance or changed its shape a certain distance, and it is now pushing up on my hand with a force of 10 newtons, and it's reporting that to us with its dial. Here now I've distorted it farther. It's pushing back on my hand with 20 newtons. Weight isn't involved in this at all. There's no weight story. This is simply a force story. The platform and I are pushing on each other with 20 newtons of force now, 30 newtons, 40 newtons, 50 newtons. And to get a 50 newton force out of this spring scale, I have to distort the spring 5 times as far as I did back when it was only pushing on me with 10 newtons. So when we put a book on there, of course, now weight becomes part of the story. The book is being supported by the spring's weight, by the spring's force. The spring's force is 29 newtons, and that then must be the weight of the book. So this is true of basically all spring scales. They take a spring that has been designed carefully, ultimately has been calibrated so that they know how hard it pushes on its own ends for a given distortion. And then they put it into a system that can read the length of the spring and also support objects, a book, a melon at the grocery store, you if you're standing on the scale. When you're supported, you or something else is supported by the spring is distorted in the process of summoning up the force it needs to support you or something else. And the readout system reads the length of the spring, the shape of the spring. And it reports that shape in units of force. Because it knows the relationship. The relationship has been determined between the distortion of the spring and how hard it's pushing on its ends. So that's the story of a spring scale. There are many various shapes of spring scale. This is one where you put the object on the scale. There are certainly ones in the grocery store where a basket is hanging from the scale. You put the objects in the basket, and a spring pulls up on those objects below it, supports their weight, and then the scale reports the weight, the force that's being used to support the object, taking advantage of Hooke's law and the fact that the scale knows how hard a pull corresponds to what sort of distortion of the spring. Even the modern electronic scales, which sort of have taken over and have eliminated a lot of the interesting visual effects involving spring scales, the electronic scales still work the same way. They have a spring inside, and that spring reports its distortion electronically. So you're still using a spring that distorts in order to summon up a force on its ends, and that force is used to support something so that the spring's distortion is related to the object's weight, and the spring's distortion is reported electronically by the deformation of some of the objects within that electronic supporting device. So, still spring scales. Well, that brings me to sort of what can go wrong with weighing. So this spring scale is not truly measuring the weight of the object itself. What the spring scale is measuring and reporting to you is how hard it is pushing on the object above it. And you just assume, when you're using the scale, that upward push of the scale on the object is the object's weight. Well, it's not really, the connections is good, but it's not literally the weight. First off, the scale's push on the object, the book in this case, is upward. So the weight is a downward force, the book's weight is a downward force on the book, the scale's push is upward, so the direction is wrong, but that's okay. We know weight's downward and we don't care. It's reporting to us 29 newtons. You could say that's 29 newton upward push of the scale on the book, but who cares? It means the book does weigh 29 newtons downward, fine. But there's a more important problem, and that is this situation where it's reporting 29 newtons and you're assuming that's the weight of the book. This assumes that the book is not accelerating. It's inertial, it's motionless and staying motionless. And then in that situation, when the book is truly inertial, the upward force on it and its downward weight do sum to zero. So reporting the scale's force on the book is just as good as knowing the book's weight. But if the book is accelerating, then that means that the net force on it's not zero, which means that the book's weight and the upward push from the scale don't cancel. And therefore, whatever the scale is reading is not the weight of the book. It's something different. And this reading the wrong value actually occurs all the time when you're weighing things. When you first put the object on the scale, it is not inertial. It is briefly bouncing up and down, and the scale is correctly reading at many different times. Each time it's telling you how hard it's pushing on the book, and because the book is not inertial, because it's accelerating and its net force is not zero, the weight of the book and the upward push from the scale are not the same. And the scale is admitting that, saying, the value is bouncing around about 29, and it's correctly telling you, I'm pushing with 33, I'm pushing with 22. It's trying all the different values. It eventually settles nicely at 29. It is now properly supporting the book. The book is now not accelerating. Everything's good. But up until that point, when it's reading 29, it's a mess, and you do not want to read the scale then. So this is why when you stand on a scale yourself and are being measured, you want to make sure that you are not accelerating. The book doesn't have a lot of control over its acceleration, but you can stand on the scale and jump up and down. And when you're doing that, you are accelerating. And what the force the scale is pushing on you with is rarely your weight. It's all over the place. And with old-fashioned bathroom scales that would read with this dial like this, I'm thinking not the electronic ones, which really don't give you a continuous idea of what the forces are. The old dial scales, they would tell you the scale's pushing very hard on you, the scale's pushing very soft on you, back and forth about your actual weight. So you had to stand still and let the scale settle down. And that brings us to what is happening during that settling down process. When you first put the object on the scale and you let it bounce a few times and eventually it settles. What's going on there? Well, if we think about, let me take a smaller object to put on the scale so I'll put a baseball on a spring. And what I'll do is of course, I can put it on, it can bounce around and settle. It's actually having trouble going side to side, but eventually it will settle down right there, be happy as a clam. And at this point, the spring is perfectly supporting the weight of the ball. Net force on the ball is zero, it's inertial. And if we measured the distortion of that spring, we knew the characteristic of the spring, how hard it pushes for a given distortion, we could have determined the weight of the ball just by measuring the spring. But during the landing process, and there's a bouncing process, we're all over the map. And so I'm going to carry us through that landing process very slowly. Human animation here, right? So suppose I drop the ball onto that spring. We know it'll bounce off and be all over the room, so I'm gonna keep my fingers on it, keep things under control. When I drop the ball, so imagine I drop it and now it's falling. It's going faster and faster and faster downward, and it has a net force downward on it that is its weight, that is accelerating downward, the famous acceleration due to gravity, 9.8 meters per second squared, and then it touches the spring. Well, when it first touches the spring is not compressed. It's at its favorite length, its equilibrium shape, and so it does not push on its own ends. The force it exerts on its own ends is zero. They're happy. And so the ball, which first touches those ends, feels no force. It isn't until the ball has descended further, because after all, it's moving downward velocity, and it's accelerating downward due to its weight and the acceleration due to gravity. So it continues moving downward, and it begins to compress the spring. As it does, the spring begins to push upward on the ball, very gently at first, and then more and more and more and more, until finally the spring end has been compressed enough to perfectly support the ball's weight. So that's the first descent towards equilibrium. The equilibrium I have in mind now is not the raw equilibrium of the spring itself. Rather, it's the equilibrium that the ball and spring will eventually settle into when they're allowed to become inertial, when time has passed, and we'll see that they eventually will settle down in this new equilibrium where the net force on everything is zero and there's no acceleration anywhere. So during the first drop to equilibrium, the ball actually accelerates downward the whole time. Even as it first touches, this will be the spring here, and this will be the top of the spring, this will be equilibrium. When the ball first touches the spring, it is no force on it. As it begins to compress the spring a little bit, now there's force on the ball. I guess I can do it with the ball, right? So now there's force on the ball, and the ball is still under supported. That is, the spring is pushing up on the ball, but not enough to balance the ball's weight. So the ball is still accelerating downward. It's still picking up speed in the downward direction, faster and faster and faster. But as it compresses the spring more and more, the support gets stronger, until finally there comes a point where, right at equilibrium, the ball is properly supported. And that's the first moment at which the ball stops accelerating. It has been accelerating downward all the way to this point, and has been picking up speed all the way to this point. So finally it's in a situation where it stops accelerating. And when it goes beyond that point, which it will because it has inertia, and because its velocity is downward, it overshoots the equilibrium. It goes too far, and it takes the spring too deep, and the spring begins to push up on the ball with a force that's greater than the ball's weight. The ball is now accelerating upward, but it's still moving downward because that's what it has been doing, and it's accelerating upward, but it's still moving downward. So the ball keeps going downward until finally there will come a moment when where the spring is now deeply compressed, is pushing up hard on the ball, and the ball is accelerating upward a lot, and it has finally run out of downward velocity, and the ball momentarily comes to a stop. It's deep into the spring is highly compressed, the ball is way over supported, so it's accelerating upward, but the velocity is momentarily zero. So there is that point in the bounce. That's the bottom of the bounce. And I guess I can do this with this spring scale. I will illustrate it. When the book first lands, very gentle push. The book is still picking up speed downward, less and less and less, perfectly supported. It stopped picking up speed, but it overshoots. And now it's too deep into the spring. It's over supported, it's slowing, stopped. So momentarily the book is no longer moving, but it's accelerating upward. And as time continues, the book rises. It's going upward faster and faster because it's being pushed upward and moving upward. It's going faster and faster and faster and faster. It's still over-supported, finally perfectly supported, but it's moving upward and it overshoots. It rises all the way up to here. Still, now it's less and less supported, so it's accelerating downward. It slows to a stop momentarily, and then it begins to descend. So it bounces up and down about equilibrium, and it eventually settles at equilibrium. So the bouncing process has some interesting features of it. I mean, it's a fascinating process. It is mathematically equivalent to most other bounces in nature, and it's mathematically then equivalent to lots of things in nature. It's one of the most well understood, most interesting to physicists phenomena there is, that rhythmic motion. It's the basis for musical instruments, for clocks, lots of things we'll see later on. But that bouncing motion has the characteristic that whenever the object is above equilibrium and undersupported, the acceleration is downward, back towards equilibrium. Whenever the object's below equilibrium and over-supported, the net force is upward, and so is the acceleration back towards equilibrium. So the object is always accelerating toward equilibrium, except, of course, when it's right at equilibrium, when it's briefly not accelerating. But the object's velocity has a different character, a phase to it. The object's velocity is each time the object reaches equilibrium and overshoots, the object's velocity is briefly the wrong way, away from equilibrium. It comes to a stop momentarily, however, and then its velocity develops toward equilibrium. And it goes back, it plows right through equilibrium, it overshoots, and because of inertia, and then it goes back the other way. So the bouncing book is always accelerating towards equilibrium, but its velocity is having trouble settling down at zero. It keeps trying, it briefly heads away from equilibrium and then comes back, then overshoots. Briefly head away from equilibrium, overshoots, back and forth and back and forth. Why does it even settle down? I mean, what keeps it moving, and why does it settle down? When it's bouncing, it has extra energy. Momentum is not so important here because it has momentum up when it's traveling upward, it has momentum down when it's traveling downward. It's pushing on things and it's transferring momentum all over the place. So following its momentum at any given time you can do it, but it's not super interesting. The book's energy, the energy involved in the system, is much more interesting. It's potentially a constant value. If there's nothing to waste energy in this system, the book will bounce forever. The book will go up and down. I guess I can stick with the book. The book will go up and down each time it passes through equilibrium. That is, it's been accelerating toward equilibrium on its way down. It gets to equilibrium, but it overshoots. And then it goes down and bounces. And then it goes through equilibrium again and overshoots. Each time it gets to equilibrium, it is traveling as fast as it will ever travel. That's its peak speed, because it's been accelerating toward the equilibrium the whole way until it gets there, picking up speed. So maximum speed occurs at equilibrium. And with maximum speed comes maximum kinetic energy. So right at equilibrium, the book has maximum kinetic energy. At the extreme ends of the bounce, top and bottom, the book is momentarily motionless and has no kinetic energy. Where'd the energy go? It's now potential energy. And the potential energy, it's because there's gravity around, it's partly gravitational potential energy, but it's primarily stored energy in the distorted spring. The actual connection between gravitational potential energy and the spring potential energy is kind of messy, and what I want to say is that there is just a potential energy. Sort of don't worry about it, whether it's gravitational or spring or some combination too. It's a potential energy, and it reaches its maximum when the book is as far away from equilibrium as possible, both the top and the bottom. So those are moments of peak potential energy, and the equilibrium are moments of peak kinetic energy. And the energy goes back and forth between potential and kinetic, potential and kinetic, potential and kinetic, as it bounces back and forth, back and forth. And if no energy vanishes from the system, or becomes thermal energy, the bouncing goes on forever. And this happens in situations, do I have a pendulum here? Not really. Such a simple thing. A pendulum. All right, pendulum. Need more weight. I love planning ahead. All right, pendulum. This, amazingly enough, has much in common with a spring scale. This is equilibrium. This is an extreme away from equilibrium, as is this. And this will go back and forth. Maximum kinetic, maximum potential. Kinetic, potential, and I'm having trouble because I'm moving my hand up here. But as it swings back and forth, the energy is going from potential, kinetic, potential, kinetic, potential, kinetic, potential, kinetic, back and forth. And it'll go back and forth like that endlessly. Really big pendulums can do that. They can go for hours and hours back and forth. They will eventually slow down because of air resistance and various other imperfections in the system. But the point is that if nothing wastes the energy of an object bouncing on a spring, it'll bounce forever. In a scale, a spring scale, that's not desirable. You don't want to have a situation where, oh, I wonder how much this book weighs. You put it on the scale and it bounces up and down. You have to wait for 20 minutes before you can read a decent value on the scale. So they deliberately put into spring scales systems to waste the extra energy. It's a little tricky because you don't want the system to also distort the reading, the value that's measured. If you put sandpaper in everything or just simply rust the whole system, yeah, it's likely to settle fast, but it might settle at the wrong value because things just don't move properly. But they manage to pull it off. They get a properly damped scale, settles down after a couple bounces, and it reads the proper equilibrium value. That's true for scales. For other systems where you actually want the bounce to continue, then they might even go to in the other direction. They try to not waste extra energy. And so they allow, for example, the pendulum of a pendulum clock. They do not want it to damp down and settle the equilibrium quickly. Click, 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 click. That's a lousy clock. So they make the pendulum that goes back and forth. They make it aerodynamic, so it slices through the air easily, streamlined. They carefully introduce bearings and stuff that don't have much friction, so they get a pendulum that swings back and forth hundreds or thousands of times before it settles significantly. So there is the story of how a spring scale measures weight. It establishes an equilibrium it supports the object at equilibrium, and it reads the force that it exerts, or its spring exerts, in order to achieve the equilibrium in supporting the object being weighed. The trick in making the measurement accurately is you got to make sure that the object is at equilibrium and that it's not bouncing up and down about equilibrium. If it's bouncing, then you'll get wacky readings because the spring will be exerting forces that are not perfectly canceling the weight of the object. And so the scale will be reading not random values, but values that are not the object's weight. And with that, I will stop talking about how spring scales work.